Okay, so I mean, it's really a great pleasure for me to talk in honor of Albert. I mean, I've met Albert many years ago, and we have collaborated in 2 papers. And when I got 60, Albert had a gift for me. His gift was the collection of quotation of our joint paper, which is actually the most quoted paper I have written. But I have a very modest contribution to this paper because it's a paper with Albert and Michael Douglas. And I mean, my contribution to the paper was to go from the main building of the Institute to the cafeteria, walking side by side with Albert. And Albert asked me a question, and in my pocket I had the answer to the question. So that was the origin of the paper. So I am extremely grateful for having the chance to encounter Albert, okay, and then to collaborate with him. And I mean, the topic of my talk, I mean, so you know what are nodes, you know what are primes, and you probably don't know what is the Adele class space, so I'm going to explain it. And somehow, if you want the origin of this talk is in the fall of this year, I was watching a talk by Peter Scholz, in which he was talking about, you know, the spec of the integers, spec z, and he was trying to draw the spectrum of the integers. So I have another picture of spec z, which I want to present. And then he was talking about some space which had been conjectured and so on. And I realized that the Adele class space was exactly answering to the questions he was asking. So then, you know, we wrote with Katia Consani a short note, which has about 10 pages and which is around since January of this year. And this is what I want to explain. So it's a very simple thing, except that, well, you have to know some mathematics and you have to know some mathematical vocabulary, I would say, mostly. But some really important things. So I will start with the analogy between knots and primes. And what we shall see is that there is a very beautiful mathematical theory which is behind the scene, which is class field theory, which is probably one of the most, according to André Weil, one of the most beautiful and amazing mathematical theory. So then I will go to the Adele class space, and eventually we shall go to drawing the spec of Z, and so on. Okay. So the starting point is something which was done by Grothendieck while he was here, essentially in the same place, except it was just the other room, okay? Because it was the room in which he was giving talks and so on. And so one of the great achievements of Grothendieck was to extend Galois theory to schemes. And I mean, in order to do that, it first reinterpreted Galois theory. You know, normally when people talk about Galois theory, they always think in terms of groups. Many people think that Galois invented groups, but this is not the case. Lagrange knew a lot of things about that. Now, but what is important is when you look at the text of Galois, is to understand that it's not just groups, it's group acting on sets. And in particular, Galois has a notion of what he calls a primitive equation. And the notion of primitive equation is not a notion which just depends on the Galois group. It depends on the action of the Galois group on the set of roots. Okay? And it's a very, very fancy notion, actually. People have tried to understand what he had in mind, but there are several possibilities on what he calls a primitive equation. Okay, so what Grothendieck has done is to then, if you want, reformulate Galois theory in terms of the category of continuous actions of the Galois group on finite sets. And then Grothendieck, after, in fact, listening to a talk by Serre in the Chevalet seminar, I think it was in '58 or something like that, then Grothendieck had the idea of the étale site, and then he introduced, if you want, in particular, the étale fundamental group, pi1 of a scheme. Now, okay, so this is a lot of mathematical vocabulary, but the only thing you have to keep in mind is a mental picture of what is an étale cover. So an étale cover for a scheme is something which is looking locally like a stack of copies of the original thing. So technically speaking, what the definition is that you have a covering by open affine sets in the base, so that when you look at the inverse image, then if you want, they are affine, and moreover, the algebra that you get from this inverse image is a finite, free, separable module over the base. So this is like the simplest possible analog, if you want, of what happens for ordinary coverings, finite. And so in particular, these groups are always pro-finite. And now, early in the 60s, when people began to compute, I mean, there was a very important contribution by Michael Artin in doing computations. And when people began to compute, they found, in fact, it's due to David Mumford and Barry Mazur in 1963, they found that there was a way to think about primes which was analogous to the way we think about knots. And I mean, in order to, if you want to implement this understanding, the important thing is to realize that there are some properties of the spectrum of Z, spectrum of the integers, which are similar to the properties of the three-sphere. I mean, but they are similar only, of course, if you think in étale terms. And the first property, which is similar to the three-sphere, is the fact that spec Z is simply connected in the sense of the étale side. And the reason why it is simply connected is very far from trivial. It's equivalent to the fact that if you take, if you want finite algebraic extensions of the rational numbers, they are ramified somewhere. Ramified means that if, for instance, the extension is defined by a polynomial and the ring of integers as what is called a power basis, then what happens is that at some prime, the corresponding polynomial reduced mod p will have a double root. That's what it means to ramifies. Okay, so there was a statement which was done by Kronecker, but which was proved by Minkowski at the end of the 19th century, and which says that for any extension, finite extension, it ramifies somewhere. Okay, and this is a highly non-trivial statement. Now, so this means that spec Z is simply connected in this sense. Okay, so this is the first point of the analogy. There is a second point, which is that when Artin and Verdier were doing computations, they found that if you take the cohomology of spec Z with coefficients in the multiplicative group, so that's a way to define a sheaf in general on any scheme, then what you find is you find Q mod Z, and you can use moreover you can use this scheme as a kind of dualizing scheme for Poincaré duality. So there is this analogy as some ground, and then if you want, okay, then there was this proposition which was done, in fact, first by Mumford, and then followed up by Mazur, and developed for many years by Morishita. So it's an analogy. It's not more than an analogy. I mean, it would be stupid to believe that to each knot you can associate a prime number. So it's just an analogy, okay? And now this analogy goes as follows. So this analogy goes like, if you want, the way we think about a knot is an inclusion of a circle in the three-sphere, all right? And the way we think of a prime is in terms of schemes. If you want, we dualize the map that goes from the integers to the integers modulo this prime. And when we dualize this map, it goes the other way. And what it does is to send, if you want, the spectrum of the finite field Fp to the spectrum of Z. So that has to be thought as the analog of the inclusion of the knot. And the knot complement corresponds to taking, if you want, to remove the prime from the spectrum of Z, okay? And now there is a crucial fact, which is the fact that actually allows you to define in the most conceptual manner what is the linking number of two knots. And this fact is the following. When you remove a knot from the three sphere, you get a space which is rather complicated and which is already an interesting invariant of the knot by taking the fundamental group. This fundamental group is in general quite complicated, but when you abelianize this fundamental group, you get something which is easy. Why? Because you have the Hurewicz theorem, which tells you that in fact it's H1. Okay, and this H1, you have then something which is the Alexander-Pontryagin duality, which, by the way, is the place where Pontryagin invented this duality for locally compact groups. So this Alexander-Pontryagin duality allows you to easily compute this H1, and you find Z. So you have this fact here that the pi1 of the complement of a knot is always equal to Z when you abelianize it. And similarly, when you go to the étale fundamental group of the complement of a prime, well, that's an interesting computation because you are looking at extensions now of Q, not which are unramified, no, but which are allowed to ramify at the prime P. And we know how they are done. They are done essentially by adding roots of unity whose order is the power of P, okay? And these are what is called the wild ramification. And the corresponding Galois group, it's a very important part of the ramification theory. The Galois group is ZP star. It's the group, if you want, of units in the ring of integers over periodic fields. Okay, so then you have the linking number, and the linking number is obtained by looking at the map from Z to Z. There is a preferred generator once you choose the orientation of the nodes, okay? And so the linking number is well defined because it's a map from Z to Z. And so similarly here you have the map from the pi1 étale of the spec FP to the pi1 étale of what happens when you remove the node. And you get the fact that, in fact, it gives you, the computation gives you this number P, which belongs to ZQ star. Okay. Now what will be interesting and which will appear is that, in fact, in the case of primes, not only you can remove one prime, you can remove all the primes except P. Okay, and this is, in fact, what the Adele class space will give you. I mean, it's not possible to remove all nodes except a given node, so it's much more discrete, if you want, in the case of primes. Okay, okay, so we shall see that. Now, yes?
So P and Q are different?
P and Q are, of course, different.
But the linking number and switching C1 and C2...
Yeah, you are right. So what people say in this development, in the analogies, they say that you shouldn't look at P in ZQ star. What you should look at is, if you want, the Legendre symbol of P in ZQ star. And then you have an antisymmetry of the Legendre symbol, which is the reciprocity law of Gauss, okay? Which mimics, if you want, the antisymmetry of the linking number, okay? But we shall come back to that, okay? All right, so now if you want, when you look at the core of the proofs of this analogy, which I showed you, you find that behind the scenes there is class field theory. Now, class field theory, as I said, it has been told by Weil, and I completely agree with him, that it's really one of the most beautiful mathematical theory. It had a very long development. At first, people were comparing the groups and showing that the groups were abstractly isomorphic. They didn't have an explicit isomorphism. And it was Artin who found the explicit isomorphism by the Artin reciprocity law and so on and so forth. And what the class field theory does, it determines, if you want, the Galois group of the maximal abelian extension of a global field. Now, instead of thinking about general global fields, you can think about number fields. So, if you want, what it does is to determine this maximal abelian extension. It's a Galois group. Rather, the Galois group itself, the maximal abelian extension is only determined in a few cases explicitly. In the case of Q, by the Kronecker-Weber theorem, and in the case of complex multiplication as well. But in general, one does not have a concrete description, but one has a completely explicit description of the Galois group, which is given by the quotient. Okay, so what is that? On the left, this is the connected component of the object, which is here. What is this object? It is called the Adele class group. And it's something which has been built by mathematicians for years and years of work. The first idea was the Kummer theory of ideals, which was coming from an analogy. Kummer had the analogy between numbers and chemistry. And the decomposition of a number as a product of primes as the decomposition of a chemical element into a combination of pure chemical elements. And in the time of Kummer, it was not possible to isolate the fluor because it was too difficult. And Kummer had an example of a field in which he had two different factorizations for the same number. I don't remember by heart, but I think it's something like it was involving square root of -5, so it's not difficult to find. And so he had these two decompositions. And then he had a fantastic idea of inventing ideal numbers that would render this factorization, the two factorization, to be in fact coming from a finer factorization. And it was sometime after Kummer, I think it was Dedekind, who invented the idea of ideal. Not ideal number, but an ideal in the concrete sense. And then, through class field theory came the idea of ideal classes, because Takagi was using ideal classes to make comparisons. And then it was, I think, Chevalet who introduced the adeles, but they all come from the same root. Adeles, and adeles, I mean, what they are, if you want, concretely defined by the GL1 group, so the group of invertible elements, in a ring, which is called the ring of adeles. And so this is the first thing that I explain when I say the Adele class space. What are the adeles? Well, the adeles are, if you want, the parent, the father, in analysis of a global field. So a global field like Q has nothing to do with analysis when you first look at it. But in fact, it has a relation to analysis, which is the following, which is that as a field, it sits discretely and co-compactly in a locally compact ring. And that's in fact a characterization of what are called global fields. So what they are, if you want, they are not themselves analytical objects, but they have a parent which is unique, and this parent is, of course, ready for analysis because it's a locally compact object. So it has an R measure, it has plenty of stuff. And it was realized by Weil, I think, and Cartier also, because Cartier gave a key idea to Weil, in fact, in the 50s, about the use of locally compact rings. So it was gradually realized that this is, if you want, the conceptual definition of a global field. All right, so now this is, if you want, the key of class field theory. But as I said, and as pointed out very strongly by Grothendieck, it's not enough to know the group. In fact, we also need group acting on sets. Okay, we need group acting on sets. And this is where the Adele class space enters the scene. So this is something which I introduced in 1996 in a contraindu note. And the Adele class space, what is it? Well, where can the group GL1 act? Well, it acts on the space. Okay? So in fact, here you can say, okay, I have the group GL1, which is the group of Adele classes. Where can I let it act? Well, I cannot let it act on adeles. No, because you have to divide, because the Adele class group is divided by the field itself, because it's a group of Adele classes, okay? So in fact, the only natural place where it acts, I mean, the most obvious, is this group is in fact acting on the quotient of adeles by the action of the field, okay? Now I remember when I explained that, when I said that, there were some people saying, "Oh, it's only that," you know. And I love the fact that when Grothendieck was writing Récolte des Semailles, he said, you know, that when there is a very simple discovery, people say it's only that. Now let me tell you why it would be totally misleading to say it's only that. Because this space, the quotient of adeles by k cross, even in the case of the rational numbers, so you take adeles over the rational numbers, this is the space we shall consider. Then you divide by multiplication. This is the prototype example of a non-commutative space. So in what sense, okay, is it a non-commutative space? It's a non-commutative space in the following very concrete sense. That if you try to construct a bijection, so this set as if you take the axiom of Zorn, I mean the axiom of the choice, this set has the cardinality of the continuum. This is not difficult to see because it's a quotient of a set which has the cardinality of the continuum. However, if you try to explicitly construct a bijection, even an injection of this set in the real numbers, you cannot do that. And you cannot do that because of ergodicity of the action of k cross on the adeles. It is ergodic for the R measure of the adeles. And so, when you try to construct a function which injects, this function will be almost everywhere constant. And so it won't be an injection, okay? And so, I mean, it is a very, very tricky space. And we shall see that we shall understand this space in two different ways, which will be complementary to each other. The first way will be non-commutative geometry. The second way will be topos theory. So it will fit, if you want, with the ideas of Grothendieck. So the first thing that happens when you take this space, this very simple space, is that when you look at the proofs in class field theory, you find that there is a fundamental principle which is the local to global. In other words, when you do class field theory, you begin by working with a much simpler case, which is a case where the global field is replaced by what is called the local field, namely a locally compact field. Locally compact fields, we are very familiar with them. They are either the real numbers, the complex numbers, or if you want, periodic numbers, extensions of periodic numbers, but they are very familiar things, okay? And when you work with these fields, the class field theory is not trivial, but it is not as difficult as the global theory, okay? So you have this very important principle. Now, how does this principle translate geometrically when you have the Adele class space? Well, it turns out that the isotropy subgroup of the Adele classes which have 0 at the place is exactly and it includes, if you want, in the global group, which is the Adele class group, exactly in the right way. Namely, this isotropy group is the way the local class field theory group includes in the global class field theory group. Okay? So this is the first remark. The second remark is that, in fact, now, with this, you understand the explicit formulas as reformulated by Weil. So if you want the explicit formulas, Riemann knew them, this is clear. Then Guinan worked on them and so on, but Weil really understood how to formulate them conceptually. And so I used to call them the Riemann-Weil explicit formulas. But how are they done? You see, in these explicit formulas, there is a very strange term, which is the integral of a function with a strange denominator. So at each place V, what you have is, you have, no, maybe I will take this one. No, it's okay, I will manage. It's okay. Okay, so in fact, if you want, what you have integrals of the form f of u over the modulus of 1 minus u, d star u. These are the local contributions over the locally compact field. So if you want, in fact, it's KV cross, it's the invertible elements. You have these terms. These terms were found by Weil. He found that they were unifying all the contributions for finite places, for Archimedean places, and so on. And now, how do they appear geometrically? They appear geometrically because you have these orbits, okay? And these orbits have a transverse space, and this transverse space is simply the local field kV. And when you look at the isotropy, so the isotropy is kV cross, and it's acting on the transverse space just by multiplication. And then what you do is, because it's a trace formula, of course, the formula which I found. So what you have to compute is the trace of this scaling operator acting on the transverse space. And the computation is extremely simple because the Schwarz kernel of the multiplication operator is delta of y minus lambda x. Okay, this is the Schwarz kernel because it replaces x by lambda x, that's all. So when you compute its trace, you are in fact computing the integral of delta of x minus lambda x because you are computing the integral on the diagonal. And you change variables and you find exactly the term 1 over 1 minus u, which is here. Okay, so I mean, for me, this was the starting point. This was really the starting point, namely the understanding that, okay, the trace, if you want the explicit formulas become a trace formula. And then what I found that if you want the zeros were appearing, the zeros of L functions with Grossen character, were appearing, but they were appearing in a very uneasy manner. They were appearing as an absorption spectrum. So, I mean, you must know that in physics, you know, spectra are the barcodes that the universe sends us. Okay, we are like in a supermarket, you know, and I mean, the stars have a barcode associated to them. This barcode is just what you get when you look at the light coming from these places. What you find is that there are dark lines in this light, missing lines, and this barcode is telling you the composition, the chemical composition of the outer atmosphere of the star. So of course, you know, it's a fantastic information. So here it appears in the same way, but mathematically this is very bothering. This is very uneasy because it appears, if you want, on a quotient space. And of course, you know, this is immediately reminiscent of some cohomology. So this was a situation a long time ago, back in '98. And if you want, the big difference with the previous understanding of spec Z is that in the previous understanding of spec Z with étale, cohomology, and so on and so forth, you don't have enough room to get the zeros of zeta because all these étale cohomology are finite dimensional. So you will never get anywhere if you try, if you want to find directly with the étale a cohomology that will do the job. Okay? What I am saying is the following. What I am saying is that now we are following another path. We are following the path of the class field theory, and we are saying that we are now extending the class field theory from groups, namely the ideal class group, to spaces. And immediately we fall on a space which gives us this. Okay, so now we want to go further, and we want to understand if this analogy between knots and primes is fitting with this. And that's what I want to explain. Okay, so how does it fit? Well, it fits because of the following. Because when you look at the Riemann zeta function, okay, the space that you have to consider is the space where, if you want the functions that you consider on the Adele class space, have a trivial behavior with respect to the maximal compact subgroup of the ideal class group. And this maximal compact subgroup is just Z hat star, namely the invertible elements in the profile completion of the integers. And so the space that you consider for zeta is this double quotient. It's not the Adele class space, which is this one, but it is this double quotient. And so what you have a projection down, of course, from the Adele class space down to this double quotient. And I mean, what we shall see is that it is exactly this projection down that will give us the understanding of this business between knots and primes. All right. And as I said from the beginning, there will be two competing theories in order to understand this space and that one. There will be non-commutative geometry, and there will be a topos. And what we found with Katia Consani in 2014 is that, in fact, if you want, this space, this double quotient, is intimately related. It is, in fact, the space of points of a topos. And this topos is incredibly simple. And I will explain what it is after a while. But this topos, what is it? It is the semi-direct product of the interval 0 infinity by the integers, where the integers act on this interval 0 infinity by multiplication. Now, if you know some music, this topos should be extremely appealing to you. Why? Because you have to think of 0 infinity as the frequencies. And the multiplication by integers is what the ear is sensitive to. Because when we multiply a frequency by 2, we are passing to the octave. And when we multiply by 3/2, okay, we are transposing. So, I mean, what we call it the frequency, the scaling side, because of the action of scaling. But what we found then is that these points of the topos are exactly this space xq, this double quotient. We also found, if you want, and I will eventually explain that, is that they form the points of the arithmetic site over the tropical semi-field. But for now, I just want to explain, to give you a mental picture which is much simpler, which is that this space, this double quotient, is in fact the space of rank 1 subgroups of the real line. Okay, you have to add also the abstract rank 1 subgroups, rank 1 groups. What is a rank 1 group? It's a group in which any two elements are commensurable. So for any two elements, you can find a multiple of one which is equal to a multiple of the other. That's all. Okay? So of course, they are all abstractly subgroups of Q, of the rational numbers. This is not difficult to see. But now you put them in the real line. Okay, so you have the rather trivial ones, which are the lattices. Okay? But you have more. And now you can ask really the naive question, which is, how can it be that this is a non-trivial space, that this is a non-commutative space? Why can't I choose one of these groups for, you know, how can I? Well, you can try, you will never do it because of ergodicity. Again, okay? So it turns out that this space of rank 1 subgroups of R is the same space as the group, as the space xq. Okay, and it is, if you want, a space that you can now begin to imagine, to have in your imagination. Okay, and now if you want, how does a prime manifest itself as a subgroup of the real line up to isomorphism? Because what you do is you take a number lambda, and you multiply this number by integers, but also you divide by powers of this prime. Okay? So this is how the prime will manifest itself. And what you will find, we shall see it immediately, you'll find that it is a periodic orbit for the action of the reals by multiplication. Okay? So here is our main theorem with Katia Consani in this little note. Okay? So here is our theorem. So our theorem is the following. Is that down on the space, we have periodic orbits, Cp. These periodic orbits, I will show them to you. They are given by the subgroups of R, which are abstractly isomorphic to the group of, the additive group of the ring 1 over P. So in other words, they are numbers of the form A over P to the n. Okay, abstractly as a group. Okay. Okay, so these, if you want, these form a periodic orbit of length log p. I remember this log p from the talk of Scholz, which triggered me to this. Okay, so, and when you look at the inverse image of this periodic orbit in the above fibration, what you find is that you find exactly the mapping torus of the multiplication by the Frobenius in the abelianized étale fundamental group of the spectrum of Z localized at P. So what I have done, I have removed all knots, all primes which are not equal to P. I have removed all of them, okay? And when I have removed all of them, I have to see that my starting node, CP, is sort of linked with all of them. And it's linked in an extremely non-trivial way, because I have the mapping torus of this thing. What does it mean geometrically? It means that if I try to lift my periodic orbit to the cover, okay, I will not be able to do that. I will have a monodromy. And this monodromy will be given exactly by what the étale picture was telling us, namely the multiplication by P in this product of ZQ star, which is exactly what gives the Artin reciprocity law. Okay, so the Artin reciprocity law was difficult to come at by Artin. He knew that there was a law, and it was only because the Russian mathematician who proved I forgot. I don't have his name present.
What the Chebotarev then simply using?
Because if you want, yes, he proved the Chebotarev. It's Chebotarev. So it's Chebotarev who found the proof of the, if you want, the fact that the size of the Galois group gives you the inverse probability that the polynomial totally splits at a prime. So once Artin saw this proof of Chebotarev, then, okay, he had the right idea. Okay, so, I mean, this is what we get. Okay, this is the theorem. And now, okay, in order to give more geometric understanding of the way this periodic orbit is sitting, it's best to look at a very simple situation where we don't take adeles, it's too complicated. We just take the local fields for P and R. We take their product and we take the corresponding space. And then when you look at it, what you find is the following. You find something very interesting. You find that you have the periodic orbit. Of course, it is there. I mean, you know, this is explained in great detail in my book with Mathilde Marcoli. So you have the periodic orbit, but you also have the generic orbit. And the generic orbit will play the role of the generic point in spec Z. So, and in fact, we shall see that this will give us the best way to draw spec Z. There was some discussion at some point of how to draw spec Z. We shall see that this will give us the right drawing. So the way it looks, if you want, this generic orbit and the periodic orbit is the following, is that this generic orbit is, of course, just a line, but this line is whirling around periodically to the periodic orbit. So the periodic orbit is in its closure, and it's whirling around like this. Now, when you go a little further, when you look at several primes, you can look at several primes, only finitely many. You again have the generic orbit, okay, which is coming from the free action and so on and so forth. And you have the periodic, now you have several periodic orbits. How do they look like? They look like this. So you can really begin to wonder, how can it be that this line is whirling around several of these periodic orbits? Okay, I mean, this is very confusing. And you can understand it immediately by means of quotient spaces. Because what you do is, you know, you write what is the whirling around of one, okay, as I wrote it like this, okay. You write the whirling around of another periodic orbit, side by side with it. You write the third one, and then what do? Well, you take the equivalence relation according to which these two will be the same, these two will be the same, but not here. It's still an equivalence relation, okay? And in fact, at the level of C-star algebra, this is perfectly easy to understand. And it comes from the C-star algebra of the cross product. And so when you do that, if you want, you find that it is exactly the right picture. And it is, if you want, the closest picture you can have eventually of spec Z. Now, of course, people think of spec Z as a bunch of points, okay, for each prime. But this is a naive picture. It's a naive picture. Why? Because if you look at the analogy with function fields, you will find out that for function fields, a place of the function field is not a point of the curve. When you take function fields, so if I take a function field, okay, and if I take a place of a function field, okay, then, so a place, it's not a point of the curve. No, a place it's an orbit of the Frobenius. Okay? So what we expect, of course, is in the case of Z, that the orbits of the Frobenius are circles of length log p because of the explicit formulas. Okay, and so this is a much closer picture to what we want. Now, there are étale facts which I don't want to enter into because they are a little bit technical, but the main thing that we use with Katia is a refinement of the Kronecker-Weber theorem, which says that if you take an abelian extension of Q, not only it's contained in the root of unity extension, but you can find this extension in such a way that you don't change the ramification. Okay, and this is done by looking at the local to global proof of the Kronecker-Weber theorem. It's a little bit tricky. I mean, it's not. It uses the result of Minkowski in particular. Okay, so we have this fact. Okay, so this is technical. Now, one thing that you can immediately and much more concretely describe now are, if you want, the finite abelian covers. Because when one looks at the étale site, you only consider finite covers. So here we are also going to consider finite covers. And when you consider these finite covers, they are, of course, associated to a subgroup of the units of the profile completion of Z, and of course this group is co-finite. I mean, okay, and so it's a kernel of, for instance, of a character of the hat star, but I mean the quotient by W will be isomorphic to the Galois group of the abelian extension, and then what you get, instead of taking the space XQ, which was the double quotient, if you want. So the space XQ, remember that it was the double quotient of Q cross of the adeles, if you want, by Q cross and by the hat star. But now we replace the hat star by W, which is co-finite, if you want. And of course, then we get a finite cover. This finite cover has many, many interesting properties. And in particular, it mimics the ramification. In other words, there is the following theorem that we have a contravariant functor from finite extensions, abelian extensions of Q to these covers. The finite set of places at which this cover ramifies is exactly not only the place, the primes where the extension ramifies, but you also have to add the Archimedean place. The Archimedean place automatically ramifies. Okay, so you have this, and but the picture is the following. The picture is really beautiful. The picture is that the inverse image of this circle now in this finite cover will be a bunch of circles, but each of them will have a non-trivial monodromy. Of course, these circles will correspond to the fact that when you take the extension at an unramified prime, then the prime splits. It splits into several other primes. Okay, these other primes don't have the same degree, so they don't have the same log p, if you want, because you have an extension of the residue field. And this is what you see in this picture. So this picture is extremely close to what we would wish to have in general. Okay. Now, the only drawback of this picture is that I have only been able to describe for you the abelian extensions. Okay, and of course we would like, I mean, but this is a big dream. Okay, because immediately you fall into Lagrange. Okay, so of course, I mean, you know, the drawback here is that we only have the abelian extension. So now come a certain number of questions. Okay, yes.
So this XQ, you said that is points of a topos.
Yeah, we shall come back to that at some point. Okay, so the first question I have, and I think only Gaber can answer this. The question is the following: imagine that I replace, in the thing I was telling about spec Z, that I replace the full étale site by only the abelian étale site. It's still a site because, okay, you can take co-products and so on. My question is the following: is it still true that you will have the, by one trivial, yes, certain, but that you will have the three cohomology to be like in Artin-Verdier? That's my question. I think it's true, but I don't know enough étale stuff to be able to say that.
Yeah, because of course you confuse in your talk is very informal. You did not. You have finite étale thing and you have other étale things. So
yeah, exactly.
But then you have to consider to pass to so that the field of fractions is always being the Q abelian.
Yeah.
But I'm not sure if this is a good.
Okay, I don't know. Okay, I mean this is a question. Huh?
In books anyway, various books consider this Galois group. I mean, this kind of cohomology or quotient of Galois groups. There are results about.
Yes, I don't know. I have to say I don't know. Yeah, but this is a question. Okay, so then there is of course to explore, but now I want to explain one thing which is extremely important for me, which is, if you want, the fact that the spectral realization that I had found, and which was by an absorption spectrum, is I understand now it much better as an H1, and the reason is the following. The reason is the role of the generic point in the computation of this H3 by Artin and Verdier, which I can transpose into the role of the generic orbit. And in fact, when I was obtaining this spectral realization, I was exactly using the same role of the generic orbit instead of the generic point. So the way, if you want this, so I will come back to that, but I mean the way it goes for spec Z is that for spec Z, if you want the proof of this Artin-Verdier duality and so on, it has been beautifully written by Barry Mazur in a paper of for École Normale, I think. And the proof, the main ingredient of the proof is an exact sequence of sheaves, which is that you take the multiplicative group scheme on spec Z, but you push forward the multiplicative group scheme on the generic point. Okay? And then you have an exact sequence, and the reason, of course, this exact sequence is the exact sequence of Cartier divisors, essentially. Okay? So why? Because if you want the sections of this one will be essentially, if you want, the multiplicative group Q. So and here what you do is okay. So it's really the Cartier divisors. Okay, and so then the whole point is that you have to compute the H2 in order to get the H3 by the long exact sequence. And when you compute the H2, if you know a little bit of Brouwer's theory, you will know that you are doing the computation of central simple algebras. And in fact, the key result goes back to a fantastic paper by Brouwer, AC, and Nutter in 1934 or something like that, in which they proved that every central simple algebra over Q in particular, okay, is a cyclic algebra. So I mean, this result, and is classified by Q mod Z. So I mean, this result is really the core, okay? And it's really, I mean, it's really probably the main result of class field theory, because, okay, I mean, it extends to general cases and so on. So I mean, once you know that, you can go. And it turns out that the spectral realization which I had, oh, sorry. So no, I want to go back. Okay, yes. So the spectral realization which I had found, you have to use a little bit of non-commutative geometry because it's a quotient space. So you have to use cross products and you have to use Hochschild cohomology instead of the, you know, a naive cohomology of the cross product and so on. And but then what you find is that it's really a relative cohomology of a pair, where the pair is coming from, I mean, the new ingredient of the pair is coming from the generic orbit. Okay? All right, so this is where we stand. And I mean, this gives a lot of confidence about this spectral realization. Of course, okay, I mean, then, you know, an immense amount of work has been done since then. But there one is using non-commutative geometry. Now, the topos theory is entering in a different way, because the topos theory is entering in order to try to understand from a topos theoretic point of view the geometric structure of this space XQ. Now, what you find is the following. What you find is that if you try to understand it, of course, just the topos by itself is not enough. You need to have a structure sheaf. And the structure will be the combination of the two. And what you find out is that the structure sheaf, in fact, is not a structure sheaf of rings. It's a structure sheaf of semi-rings. And I want to do a little bit of advocation for semi-rings. I mean, for people who know tropical geometry, what I will say is they know, okay? But let me do it still. Okay, so the first question you can ask is, why do you take semi-rings and not rings? Okay, that's a very natural question. Now you have to go back to Grothendieck. Grothendieck was never doing something if it was not natural to do it. And I claim semi-rings are more natural. Why? Because one thing which I learned, I think from Laurent Laforgue when he was lecturing here, is that when people talk about an abelian category, many people think that an abelian category is a category with an extra structure. But this is wrong. An abelian category is just a category. And it's a category in which it happens that the natural morphism from coproducts to products are isomorphisms. Okay, that's all. And now you can ask, okay, I take such a category. For an abelian category, you have to add one more axiom. This one more axiom is that you get groups, namely you have a minus. But the claim is that if I take a category in which the natural morphism from coproduct to products is an isomorphism, then when you look at the endomorphisms of an object, they form a semi-ring, not a ring. They form a semi-ring, not a ring. Okay, so semi-rings are natural. They are stamped. They are much more difficult to work with than rings because you don't have the minus. Okay? Now you look at the beginning of Weyl's book on number theory. And the very first pages of Weyl's book on number theory is the calculation of all finite fields. Replace field by semi-field. Do the same calculation. Amazingly, you find just one more guy. There is just one more. That's really amazing. And what is it? It's formed of 0 and 1. It's called the Boolean semi-field. 0 plus 1 is 1. 1 plus 1, what is it? Okay, can you tell me what is 1 plus 1? It's not 0 because it's written there, yeah. If it were 0, we would be dealing with z mod 2z, okay? So the only choice is 1. So 1 plus 1 is 1, all right? And that's what we call with Katia, we call it characteristic 1 because of the great paper of Jacques Tits in 1956, in which Tits was advocating for le corps à un élément. He has a section which is called le corps à un élément. All right. So anyway, you have this characteristic 1. And now in characteristic 1, you have amazing facts. You have a lemma, which is telling you that you have a Frobenius. Namely that if you take a semi-field of characteristic 1, then not only you have one Frobenius, like in characteristic P, but you have a whole collection of them. Namely, whenever you raise x to the power n, you get an endomorphism. Okay, it's a little exercise to do. I mean, if one wants to understand, one has to do the exercise by oneself, not look in books. Okay, and so you have an endomorphism. And these endomorphisms, of course, they define an action of n cross, I mean, of the monoid of positive integers. And because they define an action of the positive integers, you can look at the arithmetic site, which is, if you want, the topos, which is topos of sets with an action of n cross, endowed with a structure sheaf, which is coming from this previous, I mean, from Zmax. It's better to take Zmax. Okay, so now we have characteristic 1. We have this new guy, B, which is the Boolean. But we have also one thing which is extremely convincing, which is that now if you want the group R plus star of scaling is a Galois group. It is a Galois group of the tropical semi-field over this base B. Okay? And so what we first proved with Katia is that the space X is in fact the space of points of the arithmetic site over the tropical semi-field. And moreover, that the action of scaling, which is crucial in everything that we do, is in fact the Frobenius action on the points. Okay, so that was if you want, a very important result. And then we looked at the extension of scalars to this tropical semi-field, and what we found is this topos. So we found this topos. Now, why is this extension of scalars so important and interesting? Because this topos by itself, well, it's just like a topological space. You want to have the structure sheaf, okay? And out of extension of scalars, you get the structure sheaf. And what is it? It's a structure sheaf which is very much related to the localization of zeros of analytic functions. Namely, it is a sheaf of convex piecewise affine functions with integral slopes. So what you do is on zero infinity, you take piecewise affine functions, okay, with integral slopes. Okay, so you take functions of this type. Okay, they are convex. Okay, okay. I mean, then I will be in the ring of fractions. So you have this thing. Okay. And it's related, as I said. I mean, of course, you know, this all this stuff of characteristic one is in fact going back to Newton and the localization of zeros and so on, and what are called the Newton polygons and all that. So in fact, it's very old stuff. But what happens is the following. What happens is that then the periodic orbits. That's what we showed with Katia a long time ago. The periodic orbits are elliptic curves, in fact. So that when you endow these periodic orbits CP with the restriction of the structure sheaf, you find an object which is in perfect analogy with the Tate, the Jacobi, if you want, version of elliptic curve, which is the quotient of C by C cross by Q to the Z. Okay, so that's what you find. Okay, you find this analogy with elliptic curves, but you find something which is quite amazing, because what you find is that now the degree of a divisor is no longer an integer; it's a real number. It can affect any real values, and the dimension in the Riemann-Roch theorem is a real dimension in the sense of von Neumann. So in fact, if you want this shows, if you want the amazing richness of this framework. And so what you have is you have that the divisors, when you consider the divisors which are positive, you get that the dimension of H0 is, and you have a Riemann-Roch theorem. But I mean, in order to give some, you know, some feeling about this, I will finish very shortly. I just want to tell you that you develop the theory exactly as Cartier developed divisors. You find that the ring of fractions is related to functions which are no longer convex, which are piecewise affine and so on. And you find that, of course, the degree is defined as a usual sum, looking at the local story and so on and so forth. You have principal divisors, and the main theorem is that you have exactly the theorem that you have in an elliptic curve, except that now the degree of a divisor are the real numbers, and there is an additional invariant which is in z divided by p minus 1z. Okay, so I think I will just end here. Thank you.
Are there questions? Maxime.
Actually, those very fast invariant. What is HP? Because you
Sure. No, I was. So HP here is this group Z of 1 over P, additive group. Numbers with a prime divisor. And I mean, the really important thing is how the dimension is defined. It's defined like for, there are theta functions. So what you do is you take the Tate version of theta functions and you copy it by replacing the operations that we know by the operations in the tropical semifield. And you find theta functions, they satisfy all the right properties and so on. So we have a very satisfactory theory here. Right. Exactly. Yeah, sure, because you are in the fraction field. Okay.
So I missed this comment on von Neumann real dimensions. Go back to for Neumann, you said.
I go back to which offer?
So something where you mentioned real dimension in sense.
Oh yes, real dimensions. You are right. Let me mention real dimensions. Yes. No, it's not here. What? Wait. Yeah. So the real dimension is coming from the p-adic filtration of the H0, for instance. And the real value dimension is defined like this. So the dimension is defined as the limit when n goes to infinity of p minus n times the topological dimension. So this topological dimension is the most trivial dimension. It is the number of parameters that you need to parameterize the solutions. Okay, so yeah, okay. So of course, when you increase this filtration, this topological dimension increases, but it increases like powers of p. And when you divide by this power of p, you get the real dimension. And this is imitating exactly what von Neumann was doing to define the real dimension. It's on the nose. It's really the same. So it's really the same as von Neumann idea, except of course that we are dealing with characteristic one, not with complex numbers. Okay, but otherwise it's the same idea.
So one question. Oh, Maxime? Oh, please.
Yeah.
So you do not get the higher cohomology of this elliptic?
No, here if you want, okay, I mean you can say that we are cheating because we are using Serre duality to consider H1. Now we have of course worked a lot on that, but okay, this is another lecture, okay? Because what we have with Katia-Consani, for instance, is the Riemann-Roch theorem for the ring of integers Z, in which the dimensions are integer valued. Okay, and there the main difficulty was to define H1, not by Serre duality, but to define H1 really. Okay.
And for the topos, you get something on the value also.
Sorry.
For the topos, for the points of topos, on the left you have points of topos.
Yeah.
But how about on the value on the?
Oh yeah, sure. Okay. If you want, there is an open question, which is the most important, I think, which is to characterize these covers I was giving you of the scaling site, which is a topos with okay. Characterize these covers by some abstract property, because then the advantage would be that you could consider non-abelian covers. If you would consider non-abelian covers, this functor which I had described, which goes from finite abelian extensions of Q to covers, could be extended, and of course that would be you know, a big thing. But class field theory is restricted to abelian, okay? And if you, I mean, the actual mantra about extension of class field theory to the non-abelian case is the Lagrange program, which doesn't go at all in the same direction, because the Lagrange program is something which understands, if you want, the group by its representations, okay?
How could you link it to representation?
Sorry?
How could you link this to representation?
I don't know. I mean, what I know is that these covers, in fact, are the correct structure. If you want, when you look at the scaling site, it's a topos, okay? But it has this collection of covers. So in fact, its topology should be enriched using this collection of covers. This is the simplest thing to do, okay? And when you do that, of course, then what you will find out is that the spectral realization gives you some kind of étale story, but abelian. In other words, what I had shown is that you get the zeros of the L functions with Grossen character. So you get a cohomology which is equivariant with respect to the abelianized Galois group, not with respect to the full Galois group. So you are still stuck in the abelian because of class field, okay? Because of class field theory. That's, so the moral, if you want, of my talk is very simple to explain. Grothendieck extended Galois theory to schemes. What we have done with Katia is to extend the class field theory isomorphism to these schemes. Very particular schemes, those which are related to spec Z. But that's what we did, okay?
Can you define again the arithmetic site?
Sorry, yes, yeah. So the arithmetic, well, it was, let me put it on the board rather. Yeah, so the arithmetic site, if you want, it is a correct way to see it. So, correct. The correct way to describe the arithmetic site is as a topos. So if you want, the topos is the dual of n cross, okay? So what does it mean? It means that as a topos, it is a topos of sets with an action of n cross. Anything you want. And this is very, of course, this is very close to what are called the lambda operations in topology, because when you have the lambda operations, that's what you have, okay? And then we endow it with a structure sheaf. Now, what is this structure sheaf? It's given by this Zmax, okay, which I will explain more, but this Zmax has a Frobenius action for each integer. So in particular, it is a sheaf over n hat cross, okay? And this is the arithmetic side. So this gadget is the arithmetic side. Now, what is a Zmax? Okay, it's an exercise. So it's an exercise. Show that there exists only one semi-field. Only one semi-field whose multiplicative group is infinite cyclic. So this is an exercise. It's an exercise. You know that finite fields are such that their multiplicative group is cyclic, okay? But it's always a finite cyclic group. So the claim is that there is only one semi-field whose multiplicative group is infinite cyclic. It is of characteristic 1. It is isomorphic to Zmax. So conceptually, this is the idea, okay? So this is the arithmetic side. Or to describe it, you can describe it by saying that if you want, as the addition is, so you take z, but you have to add minus infinity, which will play the role of 0. And you have to think of z. So if you want to think of n belong to z, secretly in your mind, you write u to the power n. Okay. Now, so the multiplication is, of course, the addition. So in fact, so what you do is you take z union minus infinity. And for minus infinity, you imagine that u to the n gives you 0. So if n equals infinity. All right, and now what you do is, so you have the multiplication, which is the addition of integers. And now you have the addition, and the addition is given by the max. So if you take two integers, n1 and n2, they have a max, okay? And this operation of max turns out to be a good semi-ring operation. And it turns out that the multiplication is distributive with respect to multiplication. I mean, you have all this thing, okay? You have all this stuff. I mean, this is completely standard in tropical geometry. I think it goes back to the 70s. I mean, you know.
No, in fact, it's Arabs invented.
Arabs, yes.
Million plus one is
yeah,
one, yeah,
sure, exactly. Yeah, exactly. Yes, exactly. I mean, it's a very. In fact, no. Yeah, I know a paper of Jacobi which did that. Yeah, Jacobi wrote a very interesting paper. You see, because the beauty of this characteristic 1 stuff is that you can take matrices. And it turns out that Jacobi wanted to solve the marriage problem. And he wrote a paper which is probably the first technical paper in characteristic 1. And what he was doing, he was using matrices. So he was using matrices whose entries were in this semi-ring. And he was working with them, and he was, I think he was proving a Perron-Frobenius theorem with that. The same proof as the fixed point proof of the Perron-Frobenius works. So if you take these entries to be in R max, now R plus max, okay, or whatever. Okay, so then what you find out is that you have the following fact. I mean, okay, then I could talk for hours, and I don't want to do that because Albert is going to talk. But let me just say one thing to Albert. You know what you find? You find that these matrices have only one eigenvalue, only one. And you know what is the conceptual meaning of this? It's classical physics. And the Russian school of Maslov and Litvinov and so on have constructed what they call a dequantization map, which goes from quantum physics to classical physics, and you get this. So you get determinism instead of the full spectrum of an operator as the possibilities in the quantum domain. It's very interesting. I mean, it's beautiful at the conceptual level. Another beauty of this theory is that when you write down the Fourier transform, you know what you find? I mean, this is found by Maslow and Lidwinow. You find the Legendre transform. So the Legendre transform that normally we don't know where to put it in a draw is just a Fourier transform in characteristic 1. That's a beauty, I think. In fact, I always advocated to some young, energetic guy to rewrite all of thermodynamics in the language of R plus max, because that's the correct language. It's a language where in thermodynamics you have variational principles, so you have the max, and you have and most of the formulas they involve the Legendre transform and so on. So there is a whole book which is waiting to be to be written, okay? And but of course it should be done with a lot of energy. And but I mean this is it's a serious business. Also, I should say that the work of Scholz and I mean all these works that they are doing. Also, I mean they gave a course here and so on with Klaus and I mean. And they are using always valuations and all that. But valuations are hand in hand with this, because the properties of a valuation are exactly telling you that you have a morphism to this characteristic 1 object, essentially. So in fact, I mean, there must be a lot of relations with what they were doing. I mean, Clausen and Scholz. Huh? But okay, I mean, if you want, I mean, these things, one has to have the ability of comparing different points of view, of accepting the point of view of others, and so on. And so this is a lot of work. Okay, I am grateful to you. Yes? Sorry?
The scaling site, what is the difference there?
Oh, with the arithmetic site. Well, the scaling site is obtained by taking the arithmetic site, let me call it A, and tensoring it with R max over the base B. That's essentially what it is, okay? It's an extension of scalars.
What is B?
B is a Boolean semifield, okay? Okay, it's a base if you want, okay? So what you do, you extend scalars. So as I said, there was a theorem telling you that the set of points, okay? But to know that the set of points is something is not the same thing as extending scalars and then looking at the point of what you obtain by extending scalars. Obtain the same, but then you gain the structure sheaf.
So do you just do it for the structure sheaf? So you have a site?
Yes, you have a site, you have a structure sheaf, then okay, there is a little bit of of work required. Yeah, the points are the same, but the structure sheaf, of course, now is lifted to this extension, which is the scaling site, and that's how you get these convex functions. So you get these convex functions.
No, but just the Grothendieck topos is the same or the different?
No, it's the same. Yeah. Yeah. I mean, it's the same. It is now 0 infinity. So now the sheaves that you get, so the topos that you get here is 0 infinity. Okay, cross and cross. So I mean, there is still n cross, but you have 0 infinity now. You have the half line. You gain the half line. Yes. Yeah. Exactly. And then you have the sheaf on the half line of piecewise affine functions. Okay? Okay, guys. Thanks a lot. Thank you.